We're going to talk about these graphs as we go. And it's super important that when you're looking at each of these graphs, that you're talking about it from a perspective of looking at the correct graph. These graphs are showing the derivative. So we need to be able to look at the level of understanding of these graphs, both above and below what we're talking about. And by above and below, I'm talking about the different levels of what it is that's going to occupy our conversations. All right. If my derivative here is positive, that means the slope of my tangent line is positive. So during this part of the graph, my slope of my tangent line is positive, which means it's increasing. So anytime that the slope of your tangent line is positive, your function's increasing. Anytime the slope of your tangent line is negative, that means your function's decreasing. So when we look at this graph shows the derivative of f prime, identify the intervals where my original graph is increasing or decreasing. Anytime that my derivative is above the x-axis, that's an increasing conversation. And what we're looking for is having some thorough answers, having some quality answers. And typically that happens when you say the word because. If you add the word because to your justifications, you will naturally propel yourself into a more in-depth understanding of why. My graph is increasing because from negative infinity up to, and I said negative 1.5. And remember, when we're talking about intervals, we're talking about x values. Which x values am I talking about? Negative infinity to negative 1.5 is where my derivative is positive. From negative 1.5 to negative 0.5, that's where my derivative is below the line. From negative 0.5 up through infinity, that's where my derivative is positive. If your derivative is positive, if the graph of your derivative has an output value that's above the x-axis, then your graph is increasing because it's positive. And your justification comes from because the derivative is greater than 0, because the derivative is less than 0. So we want to have some kind of standard of how we're answering our problems to make sure that, number one, we're communicating our understanding of the graph, and then it's clear. Today's class, we're going to start scratching away at the second derivative. And if you wanted to talk about the second derivative, then we're looking at the slope of the tangent line of this graph. So here, my graph is increasing at a decreasing rate because my derivative or my second derivative, the derivative of my derivative, is negative. Anytime that my acceleration and my velocity have the same sign, then that's when I am increasing. Here I am increasing at a decreasing rate. Here I'm increasing at an increasing rate. And then here we can talk about that slope of that tangent line, about what happens there, and we're going to have some of those conversations. Would you please, with your group, have a conversation about graph 2 and 3 and 4. Go. All right, come back. So when I look at question 2, my graph is increasing where the derivative is positive. My graph is decreasing where the derivative is negative. Make sure that when you're using interval notation, you are using it's a conversation about x's. All right. For this problem, find all relative min and max and justify. So here's our conversation here, and what I want to make sure is that we go through and talk about this. Here, my derivative is 0. At each of these places, my derivative ends up being 0. Anytime that my derivative is 0, I have the potential for a local min or a local max. So this means that my derivative is positive, meaning the slope of my tangent line. So this is when my graph is climbing and it's positive. And then my derivative hits 0. And then here is where my derivative is negative. So that means that this is going to be a local maximum because the derivative before it was positive, the derivative after it was negative. Does that make sense to you about why that happens? Okay. So here we have no sign change. My derivative was positive. No, the derivative is negative. And then it zeroes out, and then it becomes more negative. So a graph that looks like that, if my derivative is negative, my graph is falling. If it hits 0 and then goes back down again, so that's not going to be a local minimum or maximum. That's just a place where the graph kind of stalls out, kind of thing. So this is only going to be a min if my derivative sign changes and goes back up. Does that make sense? So because there's no sign change here, that means it's not a min or max. So just because my derivative equals 0 does not guarantee that you're going to get a min or max. Sound okay? So when we look here, our critical points, and this is going to be a maximum for the same reason. This is not a min or max. This is not a min or max. Here my derivative is positive, and then it's still positive after that 0. This is the time. So anytime that my derivative changes signs, my slope of my tangent line changes signs. Are we okay with that conversation? Yeah? Okay. Looking at the back, for each problem, the derivative of f is given. Find our relative min and max. So again, if this is given to you as my derivative, I'm going to find my critical points by setting it equal to 0, factoring, and coming up with those critical points. So those critical points here and here are where my derivative is equal to 0. I don't know if it's a min or a max until I test all of the intervals on either side of those critical points. It's a maximum if it goes from being positive to negative. It's a minimum if it goes from being negative to positive. Okay on 5 and 6? Yeah? This is our critical points that we're testing. All right, so when we look at 7 and 8, this is my original function is telling me to use the first derivative test. So above, they gave us the derivative, and for 7 and 8, I have to use the first derivative test. So I have to go ahead and figure out what that first derivative is. And then I have to set it equal to 0. And then I have to figure out my critical points. Once I figure out my critical points here, then I'm going to test the intervals on either side of them. For this one, when I go to take the derivative, let's go ahead and review, because what I have here is my product rule. I have x times e to the 5x. So if I have the derivative of x, that's dx over dx, times my second term, e to the 5x, plus my first term, which is x, times the derivative of this second term. So when I take the derivative of this second term, e to the 5x, the derivative of e to the x is going to be e to the x, but this 5 ends up being from the chain rule. So the derivative of e to the x is going to be e to the 5x, right? And then the derivative of what's inside is going to be 5. So this 5x, e to the 5x comes from that 5 and that x and that e to the x. I set that derivative equal to 0, and then I go ahead and I solve. And then I get this one critical point here. And then because my derivative on either side, I can go ahead and solve. Now when you talk about number 9 gets really tricky. This was kind of an accident we put this on here, so I hope you didn't find too much frustration. It's a pretty graph, which at first seems like it's going to be great. So when it talks about f being a twice differentiable function, that's kind of like they're just letting you know that it's continuous, it doesn't have any sharp turns, and that you can continue taking that derivative on that interval. And here this is talking about where I have this interval here. So far, no big deal. We do need to remember that when 1 is my input of my function, 2 is my negative 2 is my output. This here, this graph, is the graph of my derivative of my original function. That's written down here. Okay, so I'm looking at the graph of my derivative. My derivative crosses the x-axis at negative 2 and 2 and has a horizontal tangent at negative 1. So I know that my f function has 0 or has a horizontal tangent at 2 and negative 2. And then this graph has that horizontal tangent at x is equal to negative 1. So g is going to be a new function given by the function g is e to the f of x. So whatever output I get from f of x, that's what happens as my exponent on my e. So write an equation for the line tangent to the graph of g at x is equal to 1. So when I know that g has a value of 1, f of 1, input of f of 1 is negative 2. So I know an input of 1 gives me an output of e to the negative 2. So when I look at my derivative of g, I go ahead through and I find my derivative of e to the f of x times the derivative of f of x. So when I put 1 in, through all the substitution, I end up with that. So then when I write in that that's my slope, here my derivative is equal to this, the slope of my tangent line. And I use this input to write an equation using point slope form. When I go to find the average rate of change, I wind up subbing through all of this, which I guarantee you is much harder than will be on any of the tests. So if you struggled, here's your answers. But in the interest of time, we're just going to call that question a bonus. How about that? Yay! So we have a bottle that's shaped like this, and we're going to imagine that that bottle is filling up with water. So as my water comes in, and you need to know the water comes in at a constant rate. So the water's coming into the bottle at a constant rate. What I want you to do, talk with your partner, sketch a graph of the height of the water as a function of the volume of the water in the bottle. So because the water's coming in at a constant rate, my volume is increasing at a constant rate. So this here is a steady increase as it's going up. So what I want you and your partners to do is go ahead and I want you to imagine that bottle being filled up, and I want you to have a discussion about what's going to happen to the height of the water if it's coming in at a constant rate. So take a minute and talk with your group. Go. And something that can help you when it comes to imagining what's happening here is as my water fills up at a steady rate, is the size of my bottle the same the whole way up? No, so my height is going to be changing. So an interesting conversation we can have is, if this distance represents, I don't know, let's just say 1 cup of water, do you think my next cup's worth is going to be at a same increment above, a smaller increment, or a larger increment? How come? Because the bottle is skinnier. So I bet you maybe as we get taller, 1 cup is going to be a taller band because I have a smaller width. You okay with that? Because remember, my volume is increasing at a steady rate because my water is coming into the bottle at a steady rate. So if I keep filling up that bottle, maybe my next cup is going to need that much. So what is that going to do to my height? As my volume is increasing at a steady rate, what do you think is going to happen to my height? Obviously, my height's getting taller and taller and taller. Is it getting taller at a steady rate? Is it getting taller at an increasing rate? Is it getting taller at a decreasing rate? Okay. And then the conversation is, what happens once I reach here? What happens once I reach the neck of the bottle? Have you ever been trying to fill something up and it gets to the neck and you're like, oh, snap, it comes out all over the place? Has that ever happened to you? Yeah? Okay. Why is that true? Why does that happen? Because there's no more space. It's very, very skinny. But let me ask you something. Is this rate the same or increasing or decreasing? So what I want to do is I'm going to come around, I'm going to look at your graphs, and I should see on your graph exactly when this story shifts to this story. We've got a couple good ideas out there, and for the most part, a lot of us have this kind of a graph where my bottle, the height of my bottle is increasing at an increasing rate. The height of my bottle is getting taller for sure, but it's increasing at an increasing rate because my height keeps getting taller and taller and taller as that water's coming in. Does that make sense to you? So when we talk about this point right here, that's what we're going to talk about happens right here when we hit the neck. So the interesting conversation about the neck is it's increasing at a constant rate, but it's still increasing. So talk to your group mates about what that means. probably be a little steeper. You could definitely argue that because that neck of that bottle is pretty skinny. But because that height is increasing at a constant rate, and keep paying attention to the words I'm saying, if I'm increasing at an increasing rate, or if I'm increasing at a constant rate. Because when I'm looking at that height of the bottle, we're going to explore what that point is with reference to words like concavity. This has a positive concavity because it's increasing at an increasing rate. This has no concavity because it's increasing at a constant rate. There's no curve to it. All right, so take a minute and digest what I'm saying and impress me with your description of how the height of the water in the bottle increases, or how it changes as it fills up. Use the word constant, use the word increasing, use the word decreasing. All right, so come on over and look at the back. Use the graph of the function f that represents the height of the water in the bottle in terms of the volume of water in the bottle to complete the following table. Now, this is not the bottle on the front. There's a new bottle. There are so many bottles of water to talk about. So again, we have our height of the water is what's being measured as our output. We have our volume of water, and that's given to us in terms of cups. So because the change in my volume is steady, this is what shows us that my graph or that my bottle is being filled up at a constant rate. At each iteration, I'm adding the change in my volume is 1 cup. So what I want you to do with your partners and group mates is I want you, from the graph, at each volume of water, I want you to tell me what the height of the water is. And then I want you to find the change in the height, and then your average rate of change is going to be the ratio between your change in height and your change in your volume. After you complete that, I want you and your group mates talking about what do you notice about the average rates of change? How are they changing? How does this affect the shape of the graph? And so fun, here you get to draw what you think the bottle looks like that produced this graph. Are you good on that? All right, on your mark, get set, go be brilliant. We have the height of our water. Now, I struggled with some of these estimating, so if you and I don't quite agree here, that's fine. The reason why this box is between these two is because it's set up for you to find the change in the height. So from 0 to 1 cup of water, my height went up super fast. So then my rate of change from 1 to 2 was 5, 2 to 3, 2.5, 2.5, 1, 1.5, 2.5, 5, and what's that, 10, 11, 12.5? So when we're talking about my average rate of change, because each of my measurements are going up one at a time, each of these are going to be 12.5 centimeters per 1 cup. So when you're talking about an average rate of change, let's not be lazy. Let's include our units. So it's centimeters per cup, because we want to make sure that everybody knows that I'm putting in 1 cup at a time. That's my constant. So even though these two columns have the identical values, we want to make sure that 12 centimeters is one conversation, or 5 centimeters is one conversation, but 5 centimeters per 1 cup lets us know what that rate of change is. Big jump, medium jump, a little bit of a smaller jump, smallest jump. Little bigger, little bigger, little bigger, huge jump. So what we want here is, what do you notice about the average rates of change? How are they changing? And how does this affect the shape of the graph? Again, I'm looking for, same as what we did with the fan and pick. I'm looking for fluency in your discussing increasing and decreasing and the graph and the derivative and the rate of change. I'm looking for those words in your explanations. When it comes time to draw your bottle, ask yourself what's happening over here and what you see happening here. So right away, instantly, I have a great change in my height, which means the very bottom of this bottle is which one, fat or skinny? Okay, but the very, very bottom of this bottle is skinny. And then what happens as my rate does this? It's still increasing. In fact, the entire graph is increasing because I'm always putting water in and I never take any water out. So my graph and my height are always increasing because I'm always putting water into the bottle. But this is increasing at a decreasing rate. So does that mean that my bottle is growing fatter or growing skinnier? If it's increasing at a decreasing rate, is my bottle shape, like we decided way down here, it's really tiny, right? But what is it doing? Is it going in and filling up super, super fast? Look at your graph on the other side. That's when the bottle's growing up and growing up super, super fast. This is increasing at a decreasing rate, which means the shape of the bottle must get wider because each cup of water I put in gives me less and less and less growth. And it's not a constant rate of change, so it's not, they're not straight line sides, are they? Because I'm increasing at a decreasing rate. But then something happens right around here. Something happens right around here. And my bottle halfway up starts to change shape. Because now I'm getting my height, I put each scoop of water in, and my height is jumping and jumping and jumping to the point it's increasing, just almost mirroring this. So I'll leave you with that thought. When we talk about our second derivative is the rate of change of our rate of change. So we talked about that back when we were doing position, velocity, and acceleration. The acceleration is talking to us about the rate of change of our rate of change, and that's that second derivative. And what ends up happening is that second derivative gives us a conversation about concavity. So concavity ends up being a curve to our derivative function, talking about how is our rate of change changing. So when we talk about concavity and looking at that change, anytime that we have a positive concavity, and a positive concavity is when we talk about something like up like a cup. If our concavity is up like a cup, we say that that is positive, and that is because our derivative of our function is increasing. And nobody said positive, nobody said negative. It's just that the derivative of our function is increasing. So if you look at what that derivative is, we can start here and talk about the slope of the tangent line. So in each of your baskets, you should have some kind of straight edge. If you don't, let me know and I'll be glad to help you out. These ones are fun because they have a little knob on it that you can help drive it. These ones are tons of fun because they're see-through. Maybe that'll help you. But if you need a straight edge, just let me know and I'll be able to get you more. Because what we want you to do, because what I want you to do is to be able to have that straight edge represent the slope of your tangent line. Anybody else? Anybody else? Okay. I want that to represent the slope of your tangent line. Because if you look here, my derivative is very negative. If you look here, my derivative is still negative, but less negative because it's not as steep. If you look here, my derivative is 0. If you look here, my derivative is positive and kind of flat. And then if you look here, my derivative is positive and steeper. And if you look here, my derivative is positive and steeper. So we end up with conversations where we are going to use things like steep versus flat in our conversations. And we're going to also include whether things are positive or negative, increasing or decreasing. So if you look here, and if I were to keep track of what was happening with my derivative, I would say that my derivative is very negative, then it's just kind of negative, then it's 0, then it's positive, then it's very positive with being steep. Now that's just my little shorthand way of recognizing that this is where it's very steep. But do you see that each of these values as we continue on is increasing? My derivative value is increasing. It's allowed to be negative as long as it's moving to a point where it's less negative. So think about our number line here. The slope of negative 12 is very, very steep. The slope of negative 1, still negative, but higher. Slope of 0, higher than negative 12 and negative 1. And as I move up the number line, so think about what that slope value might be. And if the derivative value is increasing, then that means that you have a concave up function. We always say concave up like a cup. Concave up like a cup. All right. Next, we're going to talk about what happens when I have negative concavity, and that is going to be when it's concave down. What do you think this sentence is? Like a, yeah. All right, let's go back again and look at that slope of that tangent line. Because our negative concavity down like a frown is when my slope value is decreasing. So as I continue to draw these slopes and I go ahead and I look at my derivative, I start off at super positive and I'm going to less positive, getting flatter and flatter until I reach the point of where I've got no slope at all and I'm at 0. Then I start having a derivative with a negative value and a derivative with an even more negative value, a derivative with a more negative value. So as my derivative goes negative and then more negative, I realize that my derivative value is decreasing because it's getting smaller and smaller and smaller. I started off positive, and each slope of my tangent line gets lower, lower, lower. So let's say I start off with a derivative of positive 12. By the time I go along the continuum and I hit 0, and then I go along the continuum, I'm very negative here with a steep negative slope. All right, so take a look at these examples. Label each function as concave up or down and justify. And when we talk about justify, we want you to say, is the derivative increasing or decreasing? Because that's what we're looking for, a conversation that justifies and defends what it is you say is happening. Talk to your partners. Your mark is set, go. All right, so as you're figuring these out, go ahead and run your tangent line. I have a very negative tangent line, which then goes to 0, and then it goes to positive numbers, and it gets steeper and steeper and steeper and steeper. So because my derivative value is increasing, this is up like a cup, and it's because the derivative value is increasing. When I look at this one, I already have a positive function, but isn't it interesting? My slope of my tangent line is always positive, but do you see how it goes from being steep to flat? And it's going flatter and flatter and flatter, approaching 0. So this one's going to be concave down because my derivative value is decreasing. We don't necessarily care whether your derivative is positive or negative. What we do care is what's happening to it. Is it getting bigger or is it getting smaller? If it's getting smaller, you're going to have a concave down conversation. So when in doubt, you need to be taking your straight edges and you need to be running them along your graph. I have a very positive graph. It goes to 0, and it's getting smaller and smaller and smaller. Therefore, this is concave down, just like this one, because f of x is decreasing. My graph starts off with a negative slope, and it levels out so that it's less negative, approaching 0. So my graph value is increasing, therefore this is up like a cup. Sound okay? Are we good? All right. So if my original graph is concave up, that means that my derivative graph is increasing. If my function is concave down, then that is where my derivative graph is decreasing. So we end up with a new type of critical point, and our critical point is where your concavity changes. If I go from concave up to concave down, that happens at a point where my function goes from increasing to decreasing or decreasing to increasing. So come back to our position, velocity, acceleration graph. When my original graph was increasing and it switched to decreasing, how did I know where that critical point was? What did we look at? Say again nice and loud. Yeah. What equals 0? Yeah, where my first derivative is equal to 0. Because when my rate of change equals 0, I went from an increasing to a decreasing conversation, and that happened when my derivative had a slope, the tangent line had a slope of 0. And that's where it changed. And we call that one kind of critical point. These points of inflection are where my concavity changes, and that's going to be the point where my second derivative is equal to 0. So where my derivative is changing, where my derivative goes from increasing to decreasing. So you can add that in. So it's that point where f of x changes from increasing to decreasing or decreasing to increasing. So just like the critical point told us where this was happening, and that matched where this was happening, now we're going to have this point of inflection where we switch from being concave up to concave down, and that's going to be where our derivative of the derivative is equal to 0. So it's going to become super important that you look at whether you're looking at your original graph or your derivative graph. And we want to be super careful about what we're talking about each time. All right, let's look at this first one. For each function, estimate where the function has positive concavity, negative concavity, and points of inflection. So if we talk about my derivative here, my slope of my tangent line is positive. My slope of my tangent line hits 0. My slope of my tangent line is negative. That whole blue story is my derivative decreasing and getting smaller. Big positive, smaller positive, 0, small negative, bigger negative. So that whole story here is where f of x is decreasing. I start positive and I go negative. Once I reach this point here, my slope of my tangent line takes on a new direction. So instead of it growing more and more and more and more negative, instead of it going down like this, it changes right around that red star, doesn't it? Because now it's going to start, wait a minute, what's happening? What's happening? I'm getting less negative. I hit 0. And now all of a sudden I'm getting positive. So during these 2 points, my slope of my tangent line goes from decreasing to increasing. Here is where I'm concave down. Here is where I'm concave up. Now I'm pretty steep, but I'm flattening out to 0, and I'm going down, and I'm going down, and I'm going down. Am I ever turning around? It's so important that you see where these little dots are. That's what we call our points of inflection. And that's where the slope of our tangent line changes from increasing to decreasing. The slope The rate of change of our rate of change. All right, so this graph is a little harder. So whatever thoughts you have for this graph, you could also replicate on this graph. You want to do this one before we jump up and talk about the velocity? All right, let's talk about this one real quick. Put your straight edge up. Super steep, flat, positive, or negative? Super steep, negative, right? What does it start to do? Is it increasing or decreasing? It's getting bigger, right? I go from very negative to 0, and then I switch around to being positive. So that's going to change right around here where you see that curve switch. What's happening? Tangent line, tangent line, tangent line, tangent line. Pretty flat, 0, getting bigger. The graph of f of x is, what is it, increasing or decreasing? It's increasing, therefore, what is it? Concave up like a cup. Once I reach my start point, because think about it, if it was going to continue increasing, this graph would continue up like this. Does it do that? Does it do that? No, it changes. So my graph, my tangent line, instead of growing like this, it's, wait, we're going to, oh, wait, we're going this way now. So I go from being super positive to less positive, less positive, less positive, 0. And then once I hit 0, what do? I go negative, right? So here I am, pretty steep, flat. Now I'm going down. So my f prime of x is decreasing. Therefore, your concave what? Down. That's if I'm looking at concavity of my original graph. These next two are not my original graph. They're the graph of my derivative. Is my derivative getting the output? Is it getting smaller or bigger? My output, what's it doing? It's getting smaller and smaller and smaller and smaller, right? If my derivative is decreasing, what is it? Concave down, because my derivative is decreasing. I had a slope of 4, then I had a slope of 3, then I had a slope of 2, then I had a slope of 1, slope of 0. So here's a minimum. Or maximum. We'd have to think about positive to negative. It's a maximum. And then it is decreasing, 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 decreasing. What happens along this part? Yeah. So it's concave up because it's increasing. What's happening here? It's decreasing, so it's a positive slope at a decreasing rate. A positive slope at a decreasing rate was one of these. It's a positive slope at a decreasing rate. So this one is going to be concave down because f of x is decreasing. It's getting smaller. What's happening here? So you're going to have to be real careful about whether you're looking at the derivative function or the original function. Uh-oh, what happened there? There I am. All right, with your group mates, do this last one before we run out of time.